Hi and welcome to Unit 4, Topic 3, Video 3. We're going to focus on the Hungarian algorithm over this video series, but in particular for this video we're going to be looking at bipartite graphs and how they can help and lead towards solutions in Hungarian algorithm questions. So let's start with what a bipartite graph is. So it's a graph like you've been learning about. The difference is that it has two sets of elements that are connected to each other but not connected within their groups. Let me show you what I mean. So you might have a really simple one here where we have element A, B and C, and this is how they're usually represented, and then 1, 2 and 3, and A might connect to 1 and 2, and we can put dots here to really represent them like graphs if you want to, which is actually a little bit less common when we get to their usage. And B might connect to 2 and 3, and C might connect to 3 and 2, and we have a bipartite graph with connections. But you notice here that C never connects to B, or 3 never connects to 1. So the A, B and C are kept separate from each other, the 1, 2, 3 are kept separate from each other. This is the definition of a bipartite graph. That's what it looks like. So what we're going to do is look at how and where we might use a bipartite graph, and I'm going to show you a particular example now, which will be coming up on your screen. Okay, here we are. In a survey conducted by an online food provider, the following food preferences were indicated by 4 people about 4 different styles. So Darren's got his food preferences, Misha hers, Angelo his, and Candice has hers. So this is what the bipartite graph looks like. It's got Darren, Misha, Angelo and Candice, Mexican, Italian, Indian and Thai food. And this is the information we've got from that question, which is now in the top corner for you to have a look at the summary. So let's have a look at it. Firstly, we've got the connections labelled for our 4 people, but we can also work in reverse. So Italian is liked by all 4 people, Mexican by only 2, Indian by only 2, Thai by only 2. Candice is fairly flexible with her food, Angelo is not so flexible. Now what we're going to do is we'll use the Hungarian algorithm later on, and then we'll transfer that information once we've done the algorithm into a bipartite graph, and then we'll use that bipartite graph to solve a problem. So in this case we could, let's say we took the question a little bit further as it says, let's say we have a sample of each of these 4 types of food. And we're going to give these samples out to these guys to have a look at. So this Mexican sample we could give to Candice or to Darren and it would be fairly reasonable. But the problem is we have to make sure everybody's happy. So let's see if we can find what's called an allocation, a correct allocation that works. So in this case I'm going to say first of all we can see that Angelo, really he needs to have the Italian. It's a bit selfish of him really, but he says he only likes Italian. And that means that this one is now out, this matching is out, and this matching is out because Italian's taken. So if this top one's out, I mean Darren's left with Mexican. So Darren can't have the Italian, so he's got the Mexican, which means that this one has matched, and that means this one's out. So Candice can't have the Mexican as well. Now the problem we've got here is that Misha doesn't mind Indian or Thai, and Candice doesn't mind Indian or Thai. So we've got choices now. Those 2 are set in stone, but we could have Misha on Indian and Candice on Thai, or the other option is that we swap that around. So there's actually 2 appropriate allocations to this problem. And so I'll just sketch one of them out, and it's this one here, and then cross out the rest of the options. So there's where we are. And if we swapped it around, we get the other one. So when you solve a Hungarian algorithm question, you might find that you get multiple options that we could use. So if we come back to our original graph here, I'd just like to make one definition with you. I'm going to trying feverishly to rub these ones out, but I can't do it live video. But if I was to add a few more matchings here, let's say that one there, let's say this one here, and this one here. So now A matches with 1, 2, 3, B matches with 1, 2, 3, C matches with 1, 2, 3, and vice versa. This would be called a complete bipartite graph, because everything matches with everything. Now, it doesn't really make sense to have multiple edges, but maybe some contexts it would. I don't know any off the top of my head. But in this case, we've got a complete one because everything matches with everything else once within their 2 subsets. Well, thanks for joining me on that bipartite adventure. Hopefully you understand. And make sure that if you have any questions that you ask your teacher. All the best.